Okay, so this is module 2. I just got done showing you this, and now we are going to move to the algebra part of it. So um, first I need to give you a definition. So if I have a polynomial, and I put a little v here, meaning that polynomial might be dependent on a vector, but if it doesn't have any factors in it of lambda, then we call the order the minimal number c, integer c, positive integer, such that mu v of lambda divides lambda to the c minus 1. There's a theorem on finite fields in finite field theory that says that you can show that the c always exists. So if you do have a factor of lambda, then basically the order is going to be factor out the lambdas and then apply the previous definition. So let me run you through an example. If I wanted to find the order of 1 plus lambda cubed plus 1, well, I take 1 plus lambda cubed plus, it should be a plus 1, there, plus 1, and I expand it on Mathematica first. So I just went on Mathematica and told it to expand it. Not that I couldn't do that by hand, but I don't want to. And because I'm working mod 2, anything with 2 in it is 0, and anything that's odd will give you a coefficient of 1. So I get this polynomial here. Now this has a factor of lambda, so I can factor out that lambda, and I'm really looking at the missing piece over here next to the lambda, 1 plus lambda squared. Well, you've seen that polynomial before, because if you take a difference of cubes, then that's the piece that's left over here, the lambda squared plus lambda plus 1. So this polynomial, which is the mu tilde that they're talking about here, divides lambda cubed minus 1. So I put the 3 as the c. I made it red so that your eyes go to it. And in this case, the order of this polynomial is 3. So what's cool about this is that the orders of these polynomials are actually the period lengths. And so there's a couple things here. And this was in a paper with a really good friend of mine, Neil Calkin, who is a combinatorist who's at Clemson, and John Stevens, who was at Montclair for many, many years. John Stevens is one of the most brilliant mathematicians I've ever worked with. He graduated with a PhD in abstract algebra from the Courant Institute, and he also worked on applied mathematics for Toyota as a consultant for many years. He was a brilliant mathematician, and so I loved working with him on this project. And this we published in Fibonacci Quarterly. Okay, so what did we do? We first said, let's suppose I have an initial condition. Now, initial condition is a string or a vector of zeros and ones from z2 to the n. And mu v is the minimal annihilating polynomial of v. What that is, it's the minimal degree polynomial such that when you plug in v in for lambda, you get 0. So it's the minimal degree polynomial where v is a root of that polynomial. And this minimal degree polynomial exists by finite field theory. Take out all the factors of lambda from that v, from that mu, and what you can prove is that the cycle length is going to be the order of that minimal annihilating polynomial. Well, that's kind of hard. How am I going to find these minimal annihilating polynomials? Well, there's something called the minimum polynomial, and I'm going to tell you what that is in a second. And it's something like the characteristic polynomial. You can actually calculate it. In a graduate level class, you would actually learn about minimal polynomials. The maximal cycle length, this thing that Dennis Carney was finding on Excel, is equal to the order of the minimal polynomial. And if I factor that minimal polynomial, the other period lengths or other periods are going to be equal to orders of these factors. So, and I can actually calculate the minimal polynomial. It turns out that it is 1 plus lambda to the n plus 1. So I can directly calculate this guy. So just to give you some background, the minimal polynomial, it's a very cool polynomial. It's taught in graduate linear algebra classes. I don't think it probably was covered in your linear algebra class, but it's a minimal degree polynomial that wipes out that matrix. You do know about a polynomial that wipes out the matrix, and that's the characteristic polynomial. That's that determinant of a minus lambda I business that you worked on in algebra class and linear algebra, and you actually calculated that characteristic polynomial. And the minimal polynomial is a a factor of the characteristic polynomial. So they're related to each other. But there's a theorem and if your instructor covered it, it's really cool. You have a really cool instructor. It's called the Cayley-Hamilton theorem. And the Cayley-Hamilton theorem says the characteristic polynomial, if you plug in the matrix in for lambda, then it wipes out that matrix. So here's an example of how to calculate the order of one of these polynomials. So for n equals 17, what I would do is I would calculate the minimal polynomial, and it turns out the minimal polynomial is these two, has one factor of lambda and has these two polynomials that are factors, g1 and g2. So I actually calculate the minimal polynomial, which I know is going to be 1 plus lambda to the 17th power plus 1. So I actually know what it is. And I calculate the orders. G1 is 85 and G2 is 255. Calculating the orders is not easy, but Maple, so Matt, you worked with Mathematica. Maple is another computer algebra system, and it's very good at doing calculations over fields, finite fields. And so it would calculate these orders for us. So we wrote code inside Maple to do this for us. And that's how we were able to calculate all those periods that you saw in the table. So some quickie things that you can say right away as conclusions. First, if I have a power of 2 to the m times r, where r is an odd number, then I can tell you that the orders of the minimal polynomial are going to be 2 to the m times the order of the CDR. So that means that if I know a lower level order, then I can give you a higher level order. They have multiples of each other by a factor of 2 to the m. And I also can tell you which vectors eventually belong to the maximal cycle length. Those are the standard basis vectors that you learned about in linear algebra. 1, 0, 0, 0, 0, 0, 1, 0, 0, 0. Those are the standard basis vectors. They always will converge to the maximal cycle length. So I can I actually can iterate and find the maximal cycle length because I know what's going to go there. So for example, if I have n equals 12, I already know the cycle lengths are 1, 3, 6, and 12. For r equals 3, the cycle lengths are going to be 1 and 3. They're these two submaximal cycle lengths here. So I can embed, basically. That's what this theorem is saying. There's a lot of other people that worked on this. At the time that I published my work on this, which was around 2002 and 2003, Mark Chamberlain was looking at this in a number of different ways. And I guess we had talked about this. I have almost no memory of it now, but Fibonacci sequences show up in this and so forth. They're really cool. And one question he asked is, which maps will look like Ducci and which ones don't? We actually looked at that question later. There was an algebraist by the name of Florian Breuer from South Africa. I don't know what he's doing now, but back then he had published a number of things on Ducci. And he had a paper that was showing up in Integers, which is a pretty decent journal. Mark Chamberlain and I listed out at the time the number of open questions that were left in this problem, and those are published in the Journal of Difference Equations and Applications. And I don't think anyone's really attacked those after. I don't think so, because I still review papers on Ducci, unfortunately for me, because I also review papers in applied math, so I'm getting hit on both sides. There's someone by the name of Ryan Zehrer who studied Ducci on Rn, and he, I believe, has a paper in one of the MAA journals. I feel like I even reviewed one of his papers. So there's people still doing stuff on Ducci. For some reason, it's one of these problems that's attractive or interesting and excites people. And you might remember this name, Mikhail Mizarevich. So I was presenting my results, my algebraic results on Ducci at the Midwest Dynamical Systems seminar, which was kind of my home until I started doing applied math. And Mikhail was in the audience. And I actually told him that I was annoyed with him because he would always blurt out questions in a kind of rude way. And I said, I don't want you to do that during my talk. And he said, I promise I won't do that during your talk. But when I was giving my talk, he did do that. He said, I promised I wouldn't, but I can't help myself. I feel like I've proved something on this topic. And he was actually the first to prove that all the iterates converge to zeros and ones. As far as I know, there was a lot of this problem was hidden away in journals that were hard to look at. Like Fibonacci Quarterly doesn't have an indexing system, so you can't really dig up how many papers were written on this topic in Fibonacci Quarterly itself or called something else. It's been called all kinds of things, playing Diffie with boxes, all kinds of different things. So it's hard to track down all the stuff that's been done on this particular map. All right, with that, we end our class.